So this squeeze theorem, which we're now going to formally define, focuses on functions that are bounded, which a lot of time means the trig function. Sine and cosine, for example, are always bound between -1 and +1. But it can work just for any general function that is bounded at a specific region. So let's, as we start to lay out the definition, let's talk about a function that is bounded. So let's let h of x be less than or equal to f of x, which is less than or equal to g of x. So in other words, my function f of x is bound between h and g. And this is true for all x in an open interval containing c, the value c, except possibly at c itself. We're going to want to focus on the limit as x approaches c of our function f of x here. And you'll recall with limits, we're not actually interested in what happens at c itself, and that's also going to be true when we look at the squeeze theorem. So we've got f of x bound between h and g for all x in an open interval containing c, except possibly at c itself. And let's say the following condition is met, that the limit as x approaches c of h of x, this function right here, a lower bound, if you will, for f of x, let's say that it equals L. It exists and it equals some finite value. And that also happens to equal the limit as x approaches c of the function g of x. In other words, h of x and g of x, as I get close to c, they're headed to the same place. And what that means is that the limit as x approaches c of f of x also has to equal L by the squeeze theorem. And if this is making sense, you can already see graphically why it's called the squeeze theorem. And we'll take a look at what happens here in just a moment. So remember from the previous video, we were looking at what happens when I take the limit as x approaches 0 of x squared times the sine of 1 over x. And I can actually say, I can speak to the boundedness of this function. I know that sine of anything is bound between -1 and +1. So I can say that -1 is less than or equal to the sine of 1 over x, which is less than or equal to +1. This is true no matter what the argument of sine is. Sine by itself is always bound between -1 and +1. Well, I'm not interested in sine of 1 over x. I'm interested in x squared times the sine of 1 over x. And so I can multiply this inequality right here by x squared. And because x squared is never going to be negative, it doesn't affect anything to do with my inequalities here. I don't have to worry about multiplying by a negative and flipping things around. I can say that this statement right here is true, that -x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. In other words, the function that I'm looking at right here is bound between -x squared and x squared. Well, I can take the limit as x approaches 0 of those two outer functions. I can say the limit as x approaches 0 of the function -x squared, I can evaluate that with direct substitution. That just equals 0 if I substitute 0 in. Then if I look at the limit of this outer function, the limit as x approaches 0 of +x squared, I can evaluate that through direct substitution and also get 0. So if the two functions that this inner function is bound by are both headed to 0, then I can say, therefore, the limit as x approaches 0 of x squared times the sine of 1 over x is equal to 0 by the squeeze theorem. And I'll kind of graphically lay out what's happening, although I would encourage you to really look at this If you want to get into a more in-depth graphing tool like Desmos, it's really worth seeing what happens here. So what happens is, and I'm going to grab a couple of different colors here so that I can make sure that I show this. X squared serves as an upper bound for this function right here. All of this function is bound with an upper bound of x squared, which is just the parent function of our quadratic functions right there. It's a parabola vertex at the origin. I can say that that is y equals x squared. I can also say that the lower bound, which was negative x squared, is the same function, just reflected across the x-axis. And so what happens here, and you can see these statements right here, the limit as x approaches 0 of those two functions, you can see it goes through the origin because that's where the vertex is. Now what happens with this inner function, x squared times sine of 1 over x, I get the same behavior that I was getting earlier when the x squared wasn't there. But because the x squared is getting smaller and smaller, it's affecting the amplitude. And so what happens here is this function still oscillates, but it's always bound by this upper and lower function, which we laid out through the inequality earlier. And so even though it's oscillating faster and faster and faster, and now this is where you can see it gets that name Squeeze Theorem, even though it's oscillating faster and faster and faster, it is being squeezed down to 0. And that's why I was able to ultimately make this statement. And the same is true here as I go in that direction as well. And so that's a very kind of rough sketch of the graph of what happens here. But as I get close to 0, my function, which was x squared sine of 1 over x, it is being squeezed down to 0. And that's where this theorem gets its name, and that's how you apply it. So when you want to evaluate a limit, there's some important things that you have to say in order to use the Squeeze Theorem. The function has to be bounded in order for this to work, and then the limits of the outer functions have to match. If those two criteria are met, you can make a statement about the limit of that innermost function using the Squeeze Theorem.